Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
Go above and beyond.
they become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. My guest today is Dr. Stephanie Wright. She's a research fellow at Imperial College London. For some reason, I thought she was thousands of miles away in Australia. I don't know why, but she's in London. So we're going to talk about her research into microplastics, perhaps nanoplastics, microplastics. Stephanie, thanks for coming.
Hi, Richard. Thank you for having me.
Yeah. So what got you interested in studying this stuff?
So I did marine biology. That was my my undergraduate degree, and just loved it. I was a massive geek, went to every lecture, loved my practicals, loved learning. And someone suggested, well, my tutor there suggested I think about a PhD. And one of the sort of standout themes or modules I took was a pollution and toxicology module. And so that really triggered my interest in pursuing that kind of research further. And I came across an advert for a PhD in toxicology, or what we call ecotoxicology, at the University of Exeter. It was to study microplastics. At the time, I had no idea what they were, had never heard of them. This was back in, I think, 2011. But really fancied the challenge, fancied the opportunity, so I went for it, and that's how I got into it all.
Okay, very good. So when you were studying marine mammals and animals, did you run into microplastics? Did you encounter animals that had ingested them or gotten caught in them and killed by them?
So I was actually looking at, I was doing laboratory-based research, and I was looking at the impact of microplastics following ingestion. So I worked on marine worms, which kind of look like the earthworms that you'd find in the soil in your garden, but they live in sandy seabeds on the sort of North European, North American shores. And they just ingest sand. That's how they feed. They extract their nutrients and energy from all the bits of detritus trapped in between the sediment grains. So I was looking at what would happen if some of those sediment grains were replaced with plastic. In particular, I looked at a polyvinyl chloride microplastic, and we found it negatively impacted their feeding activity, so they were feeding less. We found it also compromised their ability to store energy, so they had reduced biochemical energy reserves as well. So we did find some pretty negative impacts on their health, and these at the time were at concentrations which were high, but overlapped with some of the highest reported for a sediment contamination.
How do you think plastics turn into microplastics?
So there's a few different processes. The sort of most prominent that we believe is sunlight exposure. So plastic litter that's out in the environment exposed to sunlight undergoes a degradation pathway. It's triggered by UV, so we call it photooxidation. And this is a sort of ongoing process when it's triggered, and it turns into what we call auto-oxidation. And throughout this process, the plastic essentially becomes more brittle, and so it can very easily fragment and shed pieces. The other way is through microbial degradation. So microbes can utilize carbon in it once it's been weakened like that, but the most prominent pathway is via sunlight exposure.
So sunlight will break some of the bonds between the polymer chains, and then it makes it brittle, and then let's say a piece of plastic mechanically smashes up against something, or sand grains wear on it, and that allows it to further come apart.
Yeah, exactly. So once it's in that brittle state, I guess any sort of mechanical stress or abrasion for that matter, will cause it to fragment microparticles. But then aside from sunlight, there's also, of course, abrasion, which can happen during use. So, for example, wearing synthetic clothing on a day-to-day basis obviously undergoes a bit of wear and tear. That's from friction, from sitting down, standing up, from walking, and that process can also cause it to fragment as well, whether it has or hasn't been exposed to sunlight.
Have people characterized the origin of microplastics? Are they predominantly from soda bottles? Are they predominantly from clothing? Does it depend on the region? Like, how many different types of microplastics are there, and what are their origins?
So there are a few key polymers. So by polymer, we mean the type of plastic, whether it's polystyrene, polyethylene, polypropylene. We generally find probably about 6 prominent polymers in the environment. So there's some main offenders, no matter where you look. So across water, sediment, soils, air, we typically always find polyethylene, polypropylene, polystyrene, often polyamide and polyethylene terephthalate. Across the literature, if you were to look at everything that's been found so far, you'd probably conclude that fibres were more common than fragments, and fibres are originating from textiles, from upholstery, clothes, etc. But it can also depend on the size distribution you're looking at. So, for example, most recent studies looking at microplastics in air actually find it in the smaller size bracket, so the smaller your particle size, sort of below maybe 150 microns or so, you'd actually find more fragments than fibres in those size brackets. So there's a few different factors at play, but on the whole, we typically say fibres are the most prominent in the environment.
Has anyone tried to argue or demonstrate that any of this could be naturally occurring, or is that impossible?
So plastics themselves are synthetic, so to be naturally occurring would be impossible. So we synthesize them from, we use petrochemicals as the carbon source. There are also plastics which we refer to as being semi-synthetic. So they're still synthesized, but in that instance, we would use plant-based material as the carbon source. And so a type of plastic which is semi-synthetic would be rayon or cellulose acetate, but it is still a synthesized plastic. Natural polymers obviously do occur, so things like naturally occurring rubber, plant material, cellulose, they're all polymers too, but obviously of natural origin. So plastics will come from a synthetic background.
Okay, I just want to be sure. And then the degradation, does anyone have a lab set up where they're exposing a bottle to sunlight, let's say, and churning it, in a drum with sand and trying to accelerate this microplastic production? Like, has anyone been able to recreate the process? I'm not calling into question that it doesn't happen, but, again, has it been recreated?
Yeah, there are a few studies actually. So I know there's a team in South Korea who do study this in a lot of detail and have essentially kind of simulated a few different environmental conditions. So I think they take a glass bottle and they'll put some sand in there and then some pieces of plastic and have it on rotation, and also have it under artificial light, so UV light, and then over time essentially they measure what's coming off. They separate their plastic particles from the sediment and look at how the size distribution's changed, and then seeing more and more small particles appear as the time goes on, and the rotation and abrasion, UV weathering occurs, indicates that microplastics are forming from the pieces of plastic inside. There's also a study that looked at nanoparticle formation. So in this instance, there was a sort of closed system. It was just a artificial seawater with polystyrene, I think polystyrene beads or granules added. And again, there was a sort of simulated wave action and UV light, and then particles were sort of measured over time, and it was shown that nanoparticles were forming. But the challenge there is proving what composition the nanoparticles are. So it's easy to show their presence, but then to say that they are actually nanoplastics is still an analytical challenge. But it does suggest that they can form in the environment.
End of the road. Is it microparticle? Is it nanoparticle? Is it even, complete degradation? Has that been observed or quantified?
It's a really good question, and it is really hard, obviously, to measure. So, yeah, there's lots of figures bandied about out there that I'm not even sure where they come from. You sometimes read it takes 450 years for a bottle to degrade, and I have no idea how anyone could ever measure that, because that's quite a long time. But whether like plastic actually ever fully remineralizes is still unknown. There's still not a laboratory study to show that these petrochemical based polymers at least can fully remineralize. And again, measuring nanoparticles in the environment and nanoplastics, so not just measuring the size of something but actually showing what it's composed of, is really, really, really challenging. And it's something that we've still not really been able to do. So I think some of the smallest sizes that we've found in the environment so far are on the order of a few microns. Then, of course, when you've got the simulated studies, it suggests that they can be smaller as well. But to find those in the environment is a real challenge.
Well, yeah, I was going to ask you how long it takes on average. Like if you have, I don't know how you quantify this, but if you have a monolithic plastic something, would you quantify that, I don't know, after a year, 10 to 15% of it would degrade to microplastic, and then after 10 years up to 20%, and after, perhaps you could quantify the breakdown of an object in that way somehow to see how long it takes, quote unquote, to, because it doesn't matter if 90% of the object's still there. If 10% is degraded and forms like 124 million microplastics, then, that's significant.
Yeah, no, absolutely. And so there are actually other fields looking at this from the other angle. So, for example, in polymer engineering and polymer design, there are people interested in the resistance. So not really the microplastics forming or how many are forming and being released, but more like the tensile strength and the resistance of the material over time. And so in that field, degradation will be measured in terms of things like loss of tensile strength, microstructural changes on the surface, lots of cracks forming and sort of crevices and things. And I guess also you could have a loss of mass as well as an indication of loss of material. But from a microplastics angle, it's still not really been defined. And I guess that is just because it's hard to replicate what goes on in the environment in the lab. So there are weathering chambers that exist, which essentially, have again, UV light. Some of them are quite advanced, and you can change the humidity inside as well. And they're meant to sort of essentially artificially weather polymers and resins and things to check their durability. But the issue is that it's very difficult to know how that translates to real world. So if you've got UV light at a certain intensity for a certain time, you can calibrate it to have an indication of what that means in terms of time outside. I think actually the standard relating it to Florida sunshine, so how long it's the sort of equivalent time exposed to Florida sunshine, which is a lot sunnier than here. But there's still a question mark over really how relevant that is and what it actually means. So there's a lot of unknowns, I guess, for us at the moment.
Well, has anyone tried to tag garbage with a little camera or at least a location sensor to see where it goes and where it sits? And I mean, you'd have to do a lot of it in order to really get a feel, but maybe there's a way to do it. I'm picturing myself as like a piece of plastic. I'd be in anaerobic conditions, aerobic, buried under stuff, uncovered, laying in water for a while, in the sun, out of the sun, churning over stuff. I mean, there's a lot of different conditions I would be exposed to if I was one of those pieces of plastic.
Definitely. That there are studies. So there are oceanographic modelers who back in the day before plastic pollution was such a prominent issue, they'd actually use sort of tagged studies to understand how the currents move, so the global ocean and how the global currents work and move and connect. So they'd send out, I don't know, I guess GIS tagged sort of, I think, floating devices, and they'd basically record where in the world they end up as a form of mapping and understanding the ocean and the currents, essentially. And all that legacy has become very important in plastic pollution research, because floating debris and floating plastic debris in particular, because it's so buoyant and so light and susceptible to long range transport, actually follows very similar patterns and paths, trajectories once it's in the ocean.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
So plastic in the ocean, we know, will typically end up, if it doesn't sink out quickly and obviously accumulate on the sea floor, will often wind its way up into these large oceanic gyres and these big circulating currents. We have about 5 of them across the North Atlantic, South Atlantic, Pacific Ocean, and Indian Ocean. And there's big rotating masses of water. We actually call they're quite similar to deserts. The core of them is fairly barren from an ecological perspective, but you do get these kind of trash vortexes circulating around. We also know the sea floor is a big sink for plastic pollution and the sediments in general, because depending on the size of the particle, things become colonized very quickly by microbes. You'll have different invertebrates and larvae settling on these particles, and that affects buoyancy, density, and encourages them to sink out of suspension. But away from the ocean, we also know there are other sinks. So we're really just starting to appreciate that land, and especially soils, are probably a microplastic sink. And that's more to do with human activity than it is to do with meteorology or natural influence. So for example, going back to the idea of clothing being a source of synthetic fibres, every time we wash our clothes in a household washing machine, there's a emission of synthetic fibres down the drain, and they actually get captured at wastewater treatment plants in sludge. And then, at least in Europe and the UK, a large proportion of that sludge, I think it's about 80%, is actually applied to agricultural fields as a soil conditioner. So whilst wastewater treatment plants are very effective at capturing, I think, upward of 90% of microplastics that come out of household waste streams, it's actually likely being reapplied to land. So we're just starting to build up this idea that at least microplastics in the environment, there's a very complex network of pathways, and it's becoming much more 3D. It's not just surface of the ocean and the sediment. We've also got this idea of microplastics in the air and cycling to land, cycling back to rivers, and it's a big messy net.
That's horrible. Net. I mean, it sounds like clothes dryers and washing machines should be should have specific filters on them to pull out the microplastics before they get into the waste stream. And then the fact that they're going into crops, I mean, I would bet, I guess, if I'm sure people have been sampled and they probably have a microplastics load inside all of us, right? Any science there?
There was a paper which came out last year which measured microplastics in human stool. So that was one I didn't want to do. I left that to others to do that. But so it was pioneering. It's the first piece of evidence to indicate that microplastics are passing through, and sort of really affirming the fact that we are exposed to these things in our diets. So this was a study in which 8 volunteers sort of scattered around the world, so geographically dispersed, each sent back to the lab. It was a lab in Vienna, sent back a sample of their feces after sort of careful collection. They had very sort of strict instructions and a special collection pack and things to avoid plastic contamination that might be occurring in the household, and 100% of these samples contained microplastics, and I think there was something like around 20 microplastics per 100 grams of stool on average.
That's crazy. What about the mechanical, the electrical properties of microplastics? I'm sure somebody's studying that. Like I know plastics are probably insulators for the most part, but when you have, countless microplastics, how do they act when they're, ingested? How do they act when they're in a given area dispersed? What do they do? Do they, disturb or create their own electric field depending on their shape or morphology of their fibers? What are they insulative in a certain way? Like, who's studying that?
It's a really good point. So in general, it's assumed that with aging and weathering and time and sort of I guess following UV oxidation and perhaps coating and attrition of mineral grains and things to their surface, it's assumed that microplastics in the environment either will have a neutral or slightly negative charge on them. It's very different in the lab. You get lots of static when you're working with pristine particles. It makes them very difficult to recognize, but generally it's assumed, at least in the environment, after if they form through prolonged weathering and aging process, that they're more likely to have a negative charge. But how that would change, or how the different conditions of the digestive tract would influence that charge, hasn't actually, well, there's no published data on it yet, let's put it that way. So there's possibly people working on it, but it's not in the public eye. But then thinking, or going back to the fibre issue, one of the most sort of recognised or famous examples of a plastic occupational disease is in the flocking industry. And flock is shortcut nylon fibre. So it's a nylon fibre polyamide. It's cut very short and it's used in upholstery to create that kind of fake suede fuzzy effect on materials. But when it's cut with a rotary mill, it can generate a very, very, very fine respirable dust, which can enter the lower lung if inhaled. And of course, if you're working in that area and there's a high concentration of it in the air, you're quite likely to. So there has been outbreaks of occupational lung disease in response to this kind of exposure. And it's been hypothesized that perhaps one of the properties that makes it, that causes this chronic inflammation of the lung is potentially because it's positively charged, because it's polycationic in terms of its surface chemistry. But again, it's just a hypothesis. No one's looked at it yet.
Well, I guess to bring us to today, everyone's wearing masks lately. Do you hypothesize perhaps they may be breathing in microfibers from the masks they're wearing?
Yeah, I think there's potential. Yeah, absolutely. If it's, it would all depend, I guess, on the weave of the textile, and whether it's woven or non-woven. So wovens are more likely to fragment, to shed, to fracture, if you like, and release fibres than non-wovens are. So it probably would, to a degree, depend on that. So yeah, I guess the weave of your textile. But it's definitely a chance that that's happening. I know there was some research sort of a few decades ago now actually looking at fibre, microfibre release from cigarette filters, because obviously cigarette filters are a sort of woven mishmash of cellulose acetate actually, so that semi-synthetic polymer. And yeah, you've got thousands of micro-sized fibres packed in there to act as a filter, and there is some evidence that microfibers can be released from those as well upon inhalation. But I guess I'm quite hesitant to say, because obviously the benefits of wearing the mask probably does outweigh, what might happen if you inhale a couple of fibers. And actually what's important with respect to inhaling anything, and especially microplastics and fibers and things, is of course their size, but not their physical size, their aerodynamic size. So how they behave as a combination of their shape, their material density, and their physical size. Because if it's only the very small particles of an aerodynamic equivalent diameter of 10 microns or below which will enter your central airway due to aerodynamics.
Gotcha. Also, too, when plastics are made, I don't imagine that they're just pure polymer chains perfectly bonded. I would think that maybe other substances are trapped in between them, and there's not perfect, plastic making, so that when it degrades, I would think there'd be islands of other material that might get unlocked and then leach into the environment. Any study there?
Yeah, definitely. So still not yet from microplastics, because it's just still, it doesn't feel like early days anymore, but it feels like the emphasis is more being on occurrence in the environment and ecological impacts. But I guess, again, it's quite hard to measure that sort of thing in a lab, because you have to really simulate environmental conditions that are never quite representative, or you can't easily replicate it, because that's a big question mark really, is for microplastics in the environment that have undergone this really prolonged aging, weathering, degradation process, do any residual additives remain inside them, or have they all leached out? So during manufacturing, obviously you have your polymer, but then you also have added to it a whole range of different chemicals that change that polymer's properties. And that's really what a plastic is. It's a heavily modified synthetic organic polymer. So polymer plus additive equals plastic. And these additives range, you have things like antimicrobials, you have flame retardants, you have UV stabilizers, heat stabilizers, you have pigments, you have dyes. So a whole range of additives that can be added to give it the properties that we recognize in the products we use. But yeah, these are all susceptible to leaching out, whether that's during its use or whether it's afterwards. And that's because the additives aren't chemically bonded to the polymer. They're added, and I guess they kind of just, the molecules sit within this matrix, this polymer matrix, but they're not chemically bonded in any way. But the leaching, there is research looking into the rates of leaching from bigger bits of plastic, and it's shown that that certain factors, so abiotic factors such as temperature, pH, can affect the rate of leaching, but then also things like whether it's leaching into a water or a lipid-rich solution. So there's some work that's looked at leaching of these chemicals from microplastics in marine invertebrates, fish and birds, and in particular this has been modelled as well as based on some laboratory-based work. And yeah, it suggests that those animals that have that are mammals essentially, that maintain physiological temperature of about 37 degrees, there's a higher leaching in gastrointestinal fluid under those conditions.
Yeah, has anyone looked at the typical body burden of microplastics or plastics? I drink from a soda bottle, I eat something off a plastic plate or a plastic fork, I wear clothing, I would think that the average person may be exposed to the additives plus the plastics plus microplastics quite a bit.
Sure, definitely. So there's a whole wealth of research that's looked into to body burdens of additives, in particular things like bisphenol A, phthalates. They've all been quite heavily studied in the past in epidemiological studies looking at concentrations in blood and urine. But the challenge is that is separating that from microplastic exposure, because those additives are actually, you're not just exposed to them because you're ingesting microplastic containing them. They're actually sort of free and in a lot of other types of matrices. So for example, dust is quite heavily contaminated with flame retardants because it migrates out of your electronic casing or your sofa upholstery and associates with, whatever's in the household dust, for example. We obviously, in terms of body burdens of microplastics, there is the human stool study which came out, which I've mentioned, which kind of confirmed we're exposed to them in our diet. And then other than that, there are really just exposure estimates based on occurrence data. So there are studies which have looked at concentrations of microplastics in bottled water, in sea salt, in shellfish, in those sorts of types of food. But the foods that have been investigated actually only represent 15% of the average American's caloric intake. So there's a whole 85% of diet that hasn't been explored yet. So what estimates we do have are also obviously underestimates.
And then I guess last question for now. I know I'm asking you about the entire fields all in one, but
that's fine.
The microbes that associate with different plastics, are there ones that tend to hang around PET versus other plastics, for instance? And depending on size, do microbes ingest them? Do they live on their surfaces? Like, what kind of interactions do you see?
So microbes definitely colonize the surface of microplastic, and that's been shown, for microplastics sampled in the middle of the ocean, on the ocean surface, or in rivers. So they do definitely have an assemblage of microbes. Up until a few months ago, I was in the camp where I thought that you get very specific strains that will favour one polymer versus another. But there has been a couple of papers, including a review paper out recently, which suggests that the microbes are less picky, and that the studies which have shown the occurrence of these types of microbes on the surface of microplastics don't have any comparative particles. They don't have a non-plastic particle to compare to. So it's hard to show that it's a preference for microplastic over something else, rather than it just being the fact that microplastic will be colonized. So I think that whole field, well, for me at least, is still up in the air, and I think there's going to be some really interesting developments over the next few years. But it's definitely fact, that microbes do colonize their surface. There have been a few strains of Vibrio which can be pathogenic on their surface, and at the moment, there's a lot of hypothesizing around antimicrobial resistance, for example, and the role of plastic pollution in spreading those genes. But as I say, I think at the moment it just needs some more science for any robust conclusions.
Yeah, you could look at, again, which microbes seem to be more prevalent in the presence of plastic, and are they using it just as a substrate, or are they, feeding off of it, eating it?
Right, yeah,
etc.
Definitely. Yeah, and I guess, there's obviously carbon in there.
I just been asking you everything there is to know, I guess, about microplastics, but what in particular is your research about at this moment?
So my research focuses on airborne microplastic pollution and human exposure and human health impacts. So kind of got three main strands of research. One's sampling and measuring microplastics in the air. We've really had to focus there on the analytical techniques, because we're really interested in the really small particles that we would and I say really small, but in relation to other particle sciences, they're not that small, still on the micron scale. But the sizes that would enter your central airway and your lower lung and lead to exposure in your respiratory tract. So we're really focused on how we measure them, how we detect them, how we sample them, developing those analytical pipelines, all with a focus on human exposure. Then in complement with that, we're interested in internal exposure. So aside from measuring them in the air, can we find any evidence of them in the body? And are there any points of accumulation? And is that where we might see, pathogenic effects, tissue response, potentially harmful impacts in people? And then alongside that, we're doing in vitro toxicology, so looking at the potential toxicity of these particles in cells, human cell lines of the airway.
Well, so are you far along into this research, or is it relatively new?
So for the last 5 years, we've really been doing the air stuff, and it's been really tough actually, because there's just so many challenges analytically in looking for these, plastics in it, right? It's not like you can, and there's not a solvent, one solvent fits all plastic. So unfortunately, it's not too easy to go and do GCMS or anything. We can't do ICP-MS because we don't have any ions. And so from the analytical side, we rely on microspectroscopy, or it has traditionally been microspectroscopy, which up until recently involved somebody in the lab looking down a microscope, looking through a sample, trying to pick out potential plastics and collect a spectrum for them, and then match it to a database to figure out what they're made of. So where we picked up is trying to improve or introduce some automation. So we've been using spectral imaging. So we've automated that process to remove the need for a person, because then that also removes the need it removes some observer bias, and it also increases our chance of seeing the smaller stuff that someone might miss just looking down a microscope themselves. We've also had to develop automated chemometrics, so the actual statistical analysis side, because spectral imaging, it just generates millions of data points per sample, which you have to make some sense out of.
Does a given fiber or plastic particle tend to attract other particles or repel them?
They get quite dirty. So that's one of the challenges when if you do use the looking down a microscope trying to pick out plastic particles part for air, because your air sample is essentially just particles, because the air is full of particulate matter, microscopic, so you can't see it, but it is. And it's things like, mineral dust, traffic pollution, soot, bits of plant detritus and things. So your sample is, it's like if you're looking, I guess, at a sort of extracted sediment sample, you'll always have some residual particles, but you're looking for particles amongst particles, and it's really challenging. But yeah, we do see particles attached to fibres. So it might be that they are carriers for other particulate matter components as well.
So what are you hoping to figure out soon in the next couple of years? Anything you're getting close to a breakthrough on?
Yeah, so I hope so. So I think consolidating our understanding of what's in the air in terms of concentration in these health relevant size fractions, that's going to be really important for understanding risk, because at the moment there's a lot of talk about the risk of microplastics to human health, and to answer that you really need to have some solid exposure data and some solid hazard data. So we're really hoping that we can really start to refine our understanding of exposure. What concentration are we exposed to? And that would be in terms of total microplastics, but then also different polymers as well. And then, in tandem with that, to really start understanding their toxicology. I'm really interested in understanding, well, firstly, if microplastics are toxic, and then secondly, if they are, what is it that's driving that? Is it the polymer, is it because they are plastic, or is it something to do with their size or their shape, or perhaps an impurity or, additive leaching from them? So really just trying to figure out what physicochemical properties might potentially make them harmful following exposure, but then also having some kind of comparative baseline to a non-plastic particle. So there's a lot of studies out there which, they're good in their own right, but perhaps only focus on polystyrene bead. And so if you're looking at a dose response to polystyrene beads, and that's the only particle you've got, and your control is no particles, how do you know that's something to do with the polystyrene, or is it something to do with just the fact that there are a lot of solid particles? And in fact, it could be any material. It's just, a stress response to persistent particles. So I really kind of want to figure out if there's a plastic effect, I guess.
Well, what's your estimate of, the body burden, or how much microplastic we're exposed to in our daily lives?
So current estimates, at least for diet, it's estimated that we're exposed to around 52,000 microplastics per year. I think that's quite conservative, because obviously it's only based on this 15% of our diet figures that we have. So there's a lot of gaps to fill. And then if you consider what's known so far about the air and what we're exposed to in the air, it bumps up to about 73,000, I think, which in terms of particles is actually quite a low abundance. So just by way of comparison, we're exposed to billions, if not trillions, of nano titanium dioxide daily through our diet, because it's used as an additive. So, pitching it like that, it seems like a low abundance, but I think at the same time, there's a lot we don't know. And all the sort of figures existing so far are for what I would call a relatively coarse size fraction. So for example, the air estimates that we have, I think the lowest particles that have been reported, are sort of 10 microns. So there's a real gap in terms of our knowledge of what the concentrations look like below 10 microns. So I think at the moment, it's a conservative estimate of about 73,000 particles per year, but I think that's really going to increase quite quickly over the next few years as we start to gain a lot more knowledge and advance not just our technological capacity, but obviously our understanding too.
I don't know if you speak to them, but when scientists, if they speak to industry, the sources of this plastic, does the industry say just go away, or are they concerned, or what's their response so far?
They're definitely concerned in that when I've been to various meetings and workshops, there's always an industry representative there. They're always from my experience at least, keen to be involved in the conversation, obviously keep up to date with things. So I think, at least for my contacts and the people I know, I'd say they're fairly active in this. But that's at least what I've been exposed to, or what I know. But whether it's sort of the full story or not, I have no idea. Yeah, I mean, but the thing is, it is really hard to pin down. So if you've got a polyamide fiber in your sample, you can't take it any further than saying it's a polyamide fiber. And so there's no, you don't have any, it could come from a carpet, it could come from your clothing, it could come from, I don't know, something else, tire, a worn down tire, for example. So it's also quite hard not just to, it's hard to pin the blame somewhere, because that is, is essentially a mystery as to where those particles have originated from. But then also, if you can match it to a supplier, is it their fault? They've made the carpet, but they didn't make the fiber. But then is it the fiber manufacturer's fault? Because obviously, there's a demand for fibers and they're incredibly useful. So it's really hard to pin the blame, I'd say. But yeah, one of the challenges is that we can't really forensically match anything beyond saying what the polymer is, what the shape is, and kind of, guessing, okay, well, polyamide's used for carpets a lot. Maybe it's come from a carpet somewhere. So I think from that element, it's also quite difficult for industry to make kind of progress, because, yeah, we don't really have any info yet, or data on these sort of key contributors or problematic items or human activities. We're still sort of working on that source apportionment of microplastics.
I gotcha. Last question. Have you ever been to the Pacific Gyres or any of the ocean gyres? Have you visited them?
I've been to the Azores, which is sort of on the edge of the North Atlantic Gyre. So I've been to the North Atlantic Gyre, or the edge of the North Atlantic Gyre. Yeah, I was very fortunate to go on a 9-day sailing trip with Pangaea Explore, who now do X-Expedition. So they do plastics, pollution, sort of citizen science cruises. I was lucky enough to get a spot as a guest scientist on there. And I have to say,
that's cool.
When you get there, like in the sea, you might see like the odd bottle floating by, which in itself is quite shocking, because you've been at sea for 9 days, haven't seen a single person, can't see land, so you're like, well, that shouldn't be there. But then with these gyres, it's not that they're like these massive floating islands of garbage. They're more, well, everybody always uses the metaphor of they're a soup, like a plastic soup. So it really is like these fragments and particles of microplastics that are in there. So it kind of looks fine when you're just looking at it from the boat. It's just when you drag the net through and you see all these bits of plastic that you kind of see, you realize the problem. But then also the Azores, the island chain, the ocean gyre, North Atlantic gyre, is circulating and directly intercepts those islands. So actually the beaches were pretty heavily contaminated, and that was quite shocking.
Right. Yeah, that's terrible. Well, very interesting. Stephanie, what's the best way for people to find out more about your work?
That's a good question. I should have I think I've got a website. Yeah, no, I do. I've got a website. So at Imperial College, if you just search my name in Imperial College, it'll link you to our my lab's webpage. I've also got Twitter. So it's @MarineSteph is my Twitter handle, which I use intermittently, but I'm not very good at keeping on top of it all. So yeah, I guess that's it. And also, I guess just having a Google for some of the papers, things that we have.
Well, that's great, Stephanie. Thanks for coming on the podcast. I appreciate it.
Thank you very much, Richard. It's great talking to you, and thanks for having me.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.